Yes, welcome, Marcin.
Hello, hello.
How are you?
I'm fine. How are you guys doing? Are you guys
Uh, we
okay?
are, we are to guide. Good. So started today
Yeah.
our fifth conference.
So good morning all. Good afternoon. It's IEEE fifth conference, fifth IEEE international conference. We are having. We are grateful to have Marcin Papretsky with us for the fifth IEEE International Conference on Recent Advances and Innovation in Engineering, ACRE 2020, organized by IEEE Delhi section and Poornima College of Engineering. Dr. Marcin Papretsky is an associate professor at the Systems Research Institute, Polish Academy of Science. He has an MS from Adam Mickiewicz University of Poznan, Poland, a PhD from Southern Methodist University in Dallas, Texas, and a Doctor of Science degree from the Bulgarian Academy of Sciences. He is a senior member of IEEE, a senior member of SAM, a senior Fulbright lecturer, and an IEEE Computer Science Distinguished Visitor. He has contributed to more than 450 publications and was invited to the program committees of over 500 international conferences. He is on the editorial boards of 12 journals and a book series. His expertise is useful for all of us. Today, he is delivering a planetary talk on topic towards age fog cloud continuum. Before handing over this session to Dr. Marcin Papretsky, I request our driving force, a director and a principal, Dr. Mahesh Bundeli sir, to felicitate Marcin Papretsky. Sir, please.
Yes, just a minute. Yeah, I welcome Dr. Marcin Papretsky to this grand event and thank him for accepting the invitation and his cooperation for organizing this particular event. Welcome, Marcin.
It's a pleasure. Hello. Yes, you can hear me. Yes.
Yes.
It's a real pleasure to be here Thank you very, very much. Of course, it would be much more fun to be in Jaipur at this moment than it is to be connected through the internet, but times are the way they are, and there is nothing we can do about it for the time being. So, real pleasure. Namaste.
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 Okay, should we start?
Yes, I'll remove my screen. Yes.
Okay, everybody, can you see my first slide?
Yes.
Okay, let me just check something because please take a snapshot of this specific screen and me because I need it for for the project. Okay, so
Yes, yes.
just screenshot of me. Okay, guys, it's, as I said, it's a real pleasure to be here, even though we are just connecting remotely. It's a beautiful morning, late morning in Warsaw, Poland. And we have 3.5 hour difference in the case you didn't know. And the presentation, I extended a little bit of my title, which is now towards Edge Fog Cloud Continuum in the next generation of IoT ecosystems. And this is because of the project about which I'm going to tell you a few words. This is joint work with my colleague Wiesiek Pawłowski. And this blue thing here is the logo of our institute. I didn't want it to crash with the logo of the project. We will come back to the project later. Okay, so what I wanted to share with you today is some historical perspective on the developments in the world of computing. And starting from the beginning, in the early days of computers, the main thing that we had was mainframe systems. Mainframe systems consisted of the central system and dummy terminals. And we are talking about actually dummy terminals, which means that the terminals were just the screen and keyboard. They didn't have any processing power, anything useful there. All input-output devices, whatever they were connected by cable. So you had, like, for instance, printer, and there was piece of cable, actual cable going to the computer. You had a plotter. Yes, there were such devices that were plotting things. You could do this. They were even color plotters, quite expensive, but they were connected by the cable to the main computer. And everything, I mean, you had disk station, it was connected by the cable to the main computer. So there was this computer thing, which was like the brain, and then everything else was sort of dummy or supporting the brain. Of course, immediately since the beginning, the process of us getting better and better in building computers started. You had mainframes that were getting smaller and smaller. Initially, they were of the size of the big room, something like long for more than 7 meters, tall 2 meters, wide almost 2 meters, filled in with electronics in the form of lamps. Then they were getting smaller and smaller. And finally, they were those new machines, which were named mini computers, which were just the size of a big refrigerator. Okay. If you go home and you see a big refrigerator, then this was the size of a mini computer. And this was big progress, of course. Then there were even getting them even smaller, and you could put them next to your desktop. So they were like the size of a small refrigerator, small office refrigerator, and this was like a workstation. So still, even then, everything was centralized. So the keyword here is centralized. There's one central location where everything happens and everything is controlled. Now, personal computing as such can be, and of course this is slightly controversial, but I would say can be traced back to August 12th, 1981, when IBM introduced IBM PC, and they named it personal computer and they used the acronym PC. So IBM PC appears on that date, and the date is sort of strange because this is the date when IBM did not want the PC. What was happening, that designers at IBM Research Center were working on this small computer, and when they presented it to their bosses, the bosses said nobody was going to use it. When they said nobody's going to use it, then there was a question what to do with it. And they were said, well, release it to the world. Maybe somebody will find it amusing. Well, everybody found it amusing. And we started to get personal computers. And partially it's because people in Taiwan, they had big electronics factories that were ready to pick up the production of those machines, make them better, faster, smaller. And so this is 81. So this is, we are talking about 81. So we are talking about 40 years ago. 40 years ago, the PC revolution started. Okay. Then 1983, which is almost 40 years ago, we have the beginning of the internet. This is the day when the first connection between three locations in California, Stanford, Berkeley, and one more, I don't remember which one, was established. First for 2, then for 3, when internet started to work. And guys, let me remind you one important thing. Even before internet, computers were connected. This is not, and if there are any young people there in the audience, remember, internet was put on top of existing networks. It was not the case that there were no computer networks. There were plenty of computer networks. They worked on the basis of telephone lines. So it worked like this. Let's say you have one computer in Jaipur, one in Hyderabad, and one in Delhi. Okay, so there is like 3 computers. And if you want them to talk to each other, you have to have a telephone line from Jaipur to Delhi, or for you, it will be the other way around. Okay, from Jaipur to Delhi, and then one line from Delhi to Hyderabad, one from Hyderabad to Jaipur, and you had this triangle, and you had 3 telephone lines dedicated to those computers talking to each other. But they were not talking intelligently. They were talking one-to-one. So if you needed to send message, you had to use the direct line, which means if one of those lines was cut, you only had connectivity like this and like this, but this line was not working. You couldn't send information. There was no way of routing of any interesting kind. Of course, it meant that if you wanted to add a computer in Ahmedabad, which is sort of from Jaipur, like here, then you needed a line from Jaipur to Ahmedabad, from Ahmedabad to Delhi, and from Ahmedabad to Hyderabad. And this was very complex and not very good. So internet was a way to dealing with things so that messages follow to the address on their own. Absolutely fantastic development. But those two brought about the change. The change can be named decentralization. So what happens? Well, everybody gets a PC. Well, of course, not everybody, because even now, not everybody has a PC. We are finding it in Poland, for instance, now that there are still places where people don't have personal computers. And when you have lockdown, this hits the least, the children from the poorest families are hit the hardest, because there is no way for efficiently to deliver schooling to them. So there is a big problem with the moments when schools are closing. But more or less PCs are becoming available. And this means that suddenly people start to work on the PC. See, previously, to do any work, you had to work on the central mainframe, mini computer, whatever. Now you can work on your desktop. On the desktop, you put a desktop PC with the monitor, with the keyboard, and you do your work locally. This changes the dynamics. However, PCs get themselves connected to the internet. This means that you can transfer files, move files between computers. There was the file transfer protocol. Few people remember FTP, but if you remember FTP, you know what it is. It's a protocol to transfer files. You start to see communication, for instance, email. Then you have IRC, which is the predecessor of all of the communicators. And then you have World Wide Web, the idea of Tim Berners-Lee, who was fed up with file management at CERN. Moreover, you can get access to resources which are out there anywhere. You can use, for instance, Telnet as the protocol, and you can type Telnet and the address of the other machine, and you can connect to it wherever it is. Now, this is a lot of change, because suddenly it's not like everything is in one location and you can do your work only in this one location. You can first do your work on the machine which is in your office on your desktop, but also you can get out and reach out to the resources which are out there. So suddenly everything is accessible. Well, not everything, but a lot of things are accessible and they are everywhere. So we have decentralization. Now, this means now that we have resources available on the internet. Okay, so whatever you connect to the internet is somehow available. If we are to move on, we need to start to think about infrastructure that would allow one to send data to the resource. So the first scenario is you have some data on your PC, you do some work, and then you send this data to some bigger computer to be processed. Okay, it can be also stored there, so you have some storage capabilities out there. Okay, some programs that you apply to your data. For instance, I had a friend who worked in computational chemistry. He worked in Jackson, Mississippi, but he was using supercomputers located in Oxford, Mississippi. And what was he doing? He was just developing the model, and then whatever he needed, he was sending the data to the machines in Oxford, and he was running this Gaussian software, which is apparently very important for people who are doing computational chemistry. And he was running the models there, getting the data back and forth, and progressing with his research. Okay. Now, also, you may develop program locally and send it to the large machine to run some experiments. So you may locally develop something and run it on a very small data, and for large data, you run it on the supercomputer. Fantastic. You can get the data from some repositories, and all this can be done. Now, how this can be done? Well, the first way that people tried to do this was what was named the grid computing. Some of you may heard this term, grid computing. Of course, if you are young, then grid computing may be something that you are like, what? Oh, there's something in the past. Yes, there was in the past, because the years for grid computing development are the end of last century, so late 1990s, early 2000. Okay, so we are talking about more or less time frame for grid computing between 1997 and let's say 2007, when people were really interested in grid computing. Now, what is grid computing? Well, the metaphor, the way to understand it is power grid. Okay, guys. If I am using my computer here, then there is electricity. This electricity is coming from somewhere. I don't know where it's produced. Is it produced? Which power plant produces it? Somewhere there is the power plant that produces it, and I am using it. And all I do is I pay for a unit of electricity, certain amount of money. Now, if you are guys there in Jaipur, there is electricity that comes to Jaipur. But now probably a lot of you connect from all over India. So if you are in Hyderabad, then there is probably a power plant near Hyderabad that is delivering electricity. If you are in Kolkata, there is a power plant near Kolkata that delivers it. But you see, you don't care. You don't care because all that you care is that there is electricity and that there is a certain number of rupees per kilowatt hour that you're gonna pay. Okay, so the idea behind grid computing was the same. The general idea is that there is a resource and you will be paying for units of use. Somehow there will be calculation of units of use of this computer, and you will pay for how much you use. Example. Okay, let's have an example here. Let's say that Poornima College decided that they don't want to pay for licenses of MATLAB because there is MATLAB is used only in the spring in some engineering courses, but in the fall semester, only few students use it and that do some, let's say, BTech thesis or project and they need MATLAB, and maybe a few faculty members use it, but the big use is only in the spring. So if there was a company in Jaipur or in India or maybe in, north eastern India that provided MATLAB services for Gujarat and Rajasthan, then maybe the payment would be like 10 rupees per hour of MATLAB use. And then Poornima, instead of buying big licenses and then running them on their own computers and paying for electricity, all this stuff, Poornima will just pay, there will be like specific bill. This is how many hours of MATLAB you used last month. This is the amount of money you pay. And maybe this would, I'm making up the 10 rupees because I don't know what would be the right economic balance, but probably there is a way to handling it. And then you pay per use. Okay. Sun Microsystems was trying to use it in the last years of its existence before it was purchased by Oracle. They were trying to charge $1 per hour of use of what they name SunGrid, and there was a powerful Sun Enterprise Server 3000 line from the 3XXX line that was available, and there was $1 per hour. You just submitted your job. The machine was quite powerful because this was like combination of a number of Sun workstations, and you had your work done. So this was the model, okay? Completely decentralized. Somewhere is a resource and you can get to it and you can use it. The problems that people found were that the existing middleware was not very good. What was happening is that there was very steep learning curve. So people who learned to use one machine within the grid, they didn't want to change. I am not talking about guys like you. All of you are most likely computer science, computer engineering, electrical engineering. For you, telecommunication. For you, use of a machine and exploring new machine and learning how to get the new machine to work for you is part of your job. However, if you think about, let's say, art professors, let's say that in your institution you have professor of art who is doing digital art and is using some software for rendering some images. Well, this person is not a computer scientist, is not a computer geek, is not a computer weirdo. This person wants to do art. So this person needs appropriate software to be able to do this. And grid software is not good enough because, for instance, if a new machine arrived, people didn't switch to it, even though the machine was much better. We have a little bit experienced with this with people from University of Huddersfield in UK, and found out there is no way faculty who were not computer science wanted to move between machines. Moreover, grid software was usually not very flexible. You see, in the previous one, I was talking that you pay per use, yes, but you need to establish certain rules for the use. And situations like this one, that you submit a job and you submit it to a certain queue on the resource, and the queue has a time limit, and you underestimate your time use, and the job crashes because the time is used. This is what happens to me. I submit a job and I say in 30 minutes it's going to be done. It comes back crashing, not enough time. Oh, so I was waiting for it to complete in the queue and so on. So I wait again for, now I give it, okay, 1 hour will be enough. And it comes back and it took 33 minutes. So look, I could have had results much earlier, but I underestimated the use by 3 minutes. Not good, because what should have happened is it should give me those 3 minutes, but not in the inflexible environment. Also, how to handle situations where your requirements for power use, for resource use, are changing day to day. One day there is very few, another day there is very high usage, and you don't balance it. Not good. So what we need is a situation where you hide from the users things, okay? They don't need to know about storage. They just have files. They don't need to know about processors. They need their jobs to be done, okay? And then they don't want to worry about time to execute their job. They want job to be done, okay? So use as much as you need. If you need a lot, you pay a lot. If you need a little, you pay a little. If you need different type of machines, we can set you up with virtual machines that will be running the way that you want, the way that you know how to run them, because they will be virtual machines, and the rest will be hidden from you. Remember, different users have different needs, okay? So this is how cloud computing is born. So cloud enables, and here is the standard definition from someplace from the internet, ubiquitous access to shared pool of configurable resources and higher level services that can be rapidly provisioned with minimal management effort. Over the internet, of course. So the resources will always be available. And you may ask, always? Okay, let me put it this way. Microsoft has 2 big data centers in Europe. One of them is in the Netherlands. One of them is in Ireland. Look, Microsoft is running those centers half empty. This means that, let's say that the total amount of resources is 100. They are making sure that non-stop the average use is at 50, and another 50, so another half of resources, whatever is the use, another half is empty, is ready in case you're gonna have a spike for need. Okay, will it be always available? Maybe yes, maybe not, but they do a lot to assure that the resources are available. But at the same time, 1 week ago, our students here who are using Amazon Web Services on East Coast in the United States were completely shut down because there was a big collapse of Amazon Web Services on East Coast of United States. This means that you may not have your resources all the time. And I will come back to this, okay? Now, delivering cloud services is competitive only if you have economy of scale. What is economy of scale? Economy of scale is something like this. Let's say that you can sell 10 units of something, and each time you will earn 1,000. Or you can sell 1,000 units and each time you will earn 10. Well, in both cases, you will earn 10,000. However, it is easier to sell things when your margin is small. But this means that you need to have a lot of customers. This means that the big players get a lot of customers and small players don't have much chance. Centralization is back. Ladies and gentlemen, if you think about it for a moment, you have three large computing infrastructures in the world right now. One is Microsoft Azure. And here, hats to the current chair of Microsoft, because this guy turned around Microsoft from an extremely hostile and hated company to the company which is now quite well received in among people. Yes, there are older people who still remember Steve Ballmer jumping around and screaming like crazy ape, but others know that Satya is running a different company. Then we have Amazon Web Services and we have Google. Three monster ecosystems. Then we have, of course, IBM Cloud, Oracle Cloud, some local clouds, but there are three big clouds that handle majority of work, which means that in some way you have three computers. If you look at it from a slightly, like meta perspective, you have in the world three large mainframes or three large computers that are doing majority of computing the whole world needs. Yes, banks will have their own infrastructures because of the protection of personal data and so on. So there will be some companies that will have their own infrastructures, but majority of computing in the world is done by three computers. Of course, you say, but Microsoft Azure consists of thousands of computers. Yes, but for you as a user, it's one single computer. It's Azure, and it's everywhere. Everything is running from the cloud, or if not everything is started to move towards the cloud. You have Skype, you have Dropbox, you have Bitbucket, you have all tools and things that Google provides. You have Lucidchart, and there is, you can ask on the internet about popular business applications. You have now Microsoft Word or Office 365, which is running from the cloud. So everything is running from the cloud. And now we start to think about the cloud. Cloud needs the data to be sent to the cloud. Okay, if you process the data in the cloud, the results exist in the cloud, which means that in many cases, things exist only in the cloud. Now, if you don't have local copy, and if you are in a situation like Amazon Web Services suddenly goes down, and you depend on Amazon Web Services, I don't think it's good, because you have a problem. You are out of luck. You are out of your data. Now, there's even more to it, because if you think about this, the question starts to be how fast you can get the data to and from the cloud. You may say, but this is very fast. Well, yes and no, depending how fast you need the results. And then you have devices. You start to see powerful devices which you have that do nothing. Okay, because everything is done in the cloud. What powerful devices am I talking about? Well, I'm not sure if anybody of you has already this unbelievable toy. I don't. But if you are talking about Samsung Galaxy S20 Ultra 5G, and by the way, I wish that Samsung would send me some money for this advertisement, but unfortunately they don't. So out of luck. This sucker has 16 gig of RAM. Guys, think about your laptops. Is it really the case that each one of you has 16 gig of RAM on your laptop? I do, but I have a new laptop. Yes, you can have on the laptop 32 or 64 gig, but you will pay an arm and two legs, and maybe you'll have to add a kidney to it. This telephone has 16 gig of RAM. Typical new phones have 3 to 5 cameras. And the Samsung has 512 gig of extra storage. Guys, think about this. My last computer was 8 to 56. Now I have 16,512, new laptop, but the phone has as much resources as my laptop does, okay? So this is unbelievable. But if I am to go completely with the cloud model, it means that I have an extremely powerful piece of hardware in my hand and it will do nothing. It's silly. Majority of phones have 10 or more, 13 or more sensors. Those sensors produce data. This data can be used. But do we send it to the cloud? No, because we would saturate the networks. Toyota vehicle, 100 million lines of computer code and multiple computers. Here you have it. All of those sensors are connected to multiple computers, okay? So you have in this car, and this is like, I don't know what car it is not a Toyota or anything, it's just a car, modern car, and it has all those sensors. And then it has computers on board that are processing this data. They are not sending this data to the cloud, or at least not immediately. It is not processed in the cloud. It is processed locally. So what we observe is sudden explosion of number of devices, things that are connected to the internet. And they start to create this new ecosystem, which is named Internet of Things. Okay? So there is more and more of them. I am not sure about this prediction here, because this prediction may or may not be wrong. On the one hand side, we have slowdown in deployments outside, but we are getting more and more of deployments anyways, because we are trying to automatize everything. So suddenly we are surrounded by sensors and actuators. Actuators are what acts on the data. So there's data from the sensor that, okay, simplest example of actuator. Let's say that you are in an air-conditioned room and you set up temperature to 21 degrees Celsius. Then you have a thermostat, which means that you have a sensor that is sensing the temperature, and if the temperature goes above 22 degrees Celsius, it will turn on the air conditioning to take the temperature down. If the temperature goes down too low, it will start heating to move it up. This means that we have fast growing number of data streams. Of course, with the growing number of data streams, there is growing volume of data that is being sent around, okay? Everywhere there are data streams. Now, some of those data streams have to be processed in maybe even real time. Maybe it is not hard real time, maybe it's soft real time. You know, the difference, by the way, for those of you who don't know, never heard those terms, hard real time is that the decision must be made within certain time frame. And if it's not, some other decision must be taken. And this is usually associated with safety critical systems, something like a nuclear power plant, that if there is something going wrong, decision must be made. And for instance, safety measure is imposed to protect the environment, to protect the power plant itself. Soft real time is that the conditions are much softer, delicate, and if there is no decision immediately, system should act as desired, but no strong measures are needed. Okay. Now, in this case, in the world today, the loop sensor cloud actuator may take too long. Then what if connection is down? What if you are in a car and the connection to the cloud is lost? You cannot have the car which is saying, we cannot drive anymore because I lost connection to the internet. I'm sorry, I mean, this is nonsense. Then the question is, do you really need to send around all of the existing data? Is it really the case that all the data which is produced by the sensor makes sense? Look, let's go back to my example with the temperature measurement. Let's say that the temperature goes like this, 21, 21, 21, 21, 21, 21. Hey, nothing changes. Do I need to send this data anywhere? Most likely not. If it goes to 22 or 23, then this is interesting data. But if the data is all the time the same, flat, it's like, who cares? Okay? So centralization doesn't work. So people said, let's use edge computing. What is edge computing? Edge computing brings computation to the location where the data is produced. Okay, so that you can have the first level where there are sensors, there will be actuators, and there will be some computations done. There will be very short local loop. Okay, here the assumptions are that edge nodes are weak, network by the edge is slower, and then you can connect to some fast fiber optics that will go to the cloud. You have a short decision loop locally, and the rest goes to the cloud. Two-layer architecture seems a very natural solution, but again, not this easy. I'm not sure how it is in India, but in Europe, people start talking more and more about 5G networking. And telecommunication companies start to think about putting 5G networks in place. Of course, now we have 5G phones, but 5G on those phones is cheating. Remember, and this is, by the way, for everybody right now. If you are buying a telephone right now and you say, oh, I will add, I don't know, 2,000 rupees to have a 5G phone, I say don't. Because even if they sell you a 5G phone, there is no actual real 5G networking in place, other than maybe at Poornima, you may have some, you know, like test deployment for students of engineering to experiment with. But other than this, forget it. This is 5G that pretends to be 5G running over 4G, but 5G is coming. And then you're gonna have patches of networks. Some networks will be faster, some networks will be slower, and you will not know which one will come by. So if you're gonna be driving through the city or walking through the city, sometimes you will not have 5G networking. Then you start to see new generation of computer hardware. The new generation of computer hardware will be something like network on the chip. Network on the chip is the new thing, something like Intel Movidius or NVIDIA Jetson Nano, where you have a chip or a small device that you plug into your laptop, and your laptop is now running a GPU. There are people who are saying that FPGAs are now becoming a viable option. This is the reprogrammable chips. We have now federated learning. Federated learning means that you're going to have groups of nodes that collaborate and groups of nodes that don't collaborate. And it's not that collaboration is a simple loop from edge to cloud and back. We are talking about various ecosystems in which there will be joint collaborative work. Everything becomes extremely heterogeneous. And then you have workflows, which are specific workflows that have to be realized. Now, this means that the future, the near future at least, looks like this. Nodes will be very different. You're going to have general purpose nodes, you're going to have task dedicated nodes, you're going to have transforming nodes. They will have various powers, various capacities, and everything will be very, very different. You're going to have highly heterogeneous networks, different hardware, different software, different speed, different protocols, and it's all gonna be within one ecosystem. Large ecosystems will have all of them, and all of them will have to work together. You're gonna have different business models to support. Guys, listen, if you're gonna have something like federated learning or collaborative work, then various parts of the ecosystem will collaborate in various scenarios. You're gonna have something that is named, and there is a new word, co-opetition. The word co-opetition I heard recently. I love the word, the sound of it, co-opetition. Co-opetition means that this is cooperation and competition. You're gonna have possibly two companies or more that in one scenario they are competing, but in another they are collaborating. And it is at the same time. So we may collaborate, but we may compete depending on the context. Okay? This means that the access control is going to be extremely important. And then there will be various workflows to realize federated learning. You just don't have simple workflows going back and forth. You're gonna have much more complex workflows. So people are now saying we're gonna have fog computing, where you're gonna have data, compute, storage, and applications somewhere between the source and the cloud. So we are getting a three-layer architecture: edge, where there are sensors and actuators; fog, which is everything in between; and cloud. Cloud, where there are resources that are unlimited. So how to make it work? Okay, here is the logistics systems example. So we have something that is like a port where a ship arrives and it has some containers. And by the way, nowadays, containers already have sensors on them. And especially if those are containers that are cooling containers, they have a lot of sensors on them. Then there is a gateway that the ship and its containers talk to in the port. And then the port talks to a tracking company and maybe a some kind of a airline. All of them talk in various scenarios.